All right. Our next question, Tom, comes from some statements you made in a very popular video just recently put out, Physics Experiments Update and Future Plans. It's the result of your first physics experiment, and the news was very exciting. There were a lot of really good and encouraging comments on that, and a couple of phrases stood out for me. There is obviously some intelligence in that process, and you're talking about the results that you're getting from the double slit experiment. It's very startling information. Could you explain this, and how could you explain this to a general audience?
Just talking about the double slit experiment by itself, nothing about the experiments I did or whatever, but just looking at the double slit experiment. Okay, the double slit experiment was very interesting in that we had optics that had been around for 100, 200 years before anybody thought about quantum physics. And they knew how to shine light through chunks of glass, through lenses, reflect it from mirrors. They had all of this, and they had theory to explain it. And that theory was wave theory. They explained it in terms of waves. And if you made that assumption that light was a wave, then there was ways that you could calculate right answers. Like you could calculate if you sent a beam of coherent light to two, so that beam of light covered both slits, you would get an interference pattern. And you could calculate exactly where that interference pattern would be, where each bright spot would be and where each black spot had no light in it, where they would be. And you'd be correct. And you could change things like the distance between the slits or the frequency of the light and recalculate it. And sure enough, if you did the experiment again with those new values, you would have it exactly right on. So they felt very confident about their idea that light was a wave. Then Albert Einstein noticed that in the photoelectric effect, light seemed to carry a discrete chunk of momenta. Okay, that made it look like a particle, like a little chunk of something that has momenta. Now, light's kind of a magic particle because it always goes the speed of light, it never goes slower, and it has no rest mass. So when it finally slows down to it's still, it has no mass. Okay, so it's got some strange characteristics. Light's kind of a unique sort of thing in physics. But in any case, the idea was that you could get a particle of light because they could see that. They could see that here a photon came and kicked several electrons out of their orbits. And another one came, kicked electrons. That's the photoelectric effect. Light comes in, electricity goes out. Well, that's because the light knocks electrons out of their orbit. And to do that takes a very specific kind of energy. And they could see that it wasn't a continuous process. It was just like happened now, and then again, and then again. It wasn't a continuous thing. So it came in chunks. So Albert saw that. I think he even got a Nobel Prize for that. He didn't get a Nobel Prize for what he's known for, which is relativity, but he got a Nobel Prize for that. And that made a big problem, logical problem for physicists. Light's a wave, light's a particle. Which is it? It can't both be true. You can't be a particle and be a wave at the same time. And they did different experiments, and they kind of came to the idea that, well, if you do wave kind of experiments, light's a wave. And if you do particle kind of experiments like photoelectric, light's a particle. And it depends on what you're doing as to whether it's a particle or a wave. It has both attributes. It can appear to be either one. And that was a thing they called the principle of complementarity. And of course, that was just because they didn't know what else to say. They didn't really understand. The double slit experiment was a result of trying to understand light better. So the one fact that they knew from optics was that if you had photons, then the photons would not be interactive. It's not like the photons stick to each other or bump into each other, knocking each other in different directions. That doesn't happen. Photons do not interact. But if that's the case, and photons do not interact, if you send one photon at a time or a million photons at a time, shouldn't make any difference because they don't interact. So if you send a million at a time, it's a million individual single photons, non-interacting, going through that slit. Okay, so now you've got something that's really interesting. So you've got the people who say light's a particle, and if you send one at a time, those particles are going to do just what particles do. They're going to pile up behind each slit because particles travel in straight lines unless acted on by some external force. There is no external force. Therefore, they must pile up behind the slits. Particles do that. So they wanted to do this double slit experiment with single particles of light and see indeed what they do. Because if you send millions of them through there, it's just like sending a million individuals that aren't interacting. There's no difference. But yet we know if you send millions through there, what happens is they act like a wave. They don't act like particles. That's shining the light on it. It's a wave, and you can make calculations and get the right answers for the wave. But we know they don't interact, and we also know they're particles, so they shouldn't be a wave. They should act like particles. So they do the double slit experiment with single particles. And they pass a particle through the slits, and that particle goes to the screen, goes through one of the slits, and ends up hitting the screen. And then you send another one through, and it ends up hitting the screen. And you keep sending them through one at a time, and each one of them hits the screen somewhere. And after you send a few hundred through, you see a pattern on the screen. And it's an interference pattern, just like light was a wave. And they said, well, all right, how is that possible? The particle must go through both slits at the same time and interfere with itself. Well, of course, that's ridiculous. Particles don't split in half and go through both slits at the same time and interfere with themselves. That's kind of a bogus idea. And they came up with other kinds of bogus ideas too. But this is what happened and why it happened. Well, let me give you one other thing then. So if they had a device, or let's say that they did, this is just a thought experiment now. So they have a device, and it measures which slit the particle went through. There's only two slits. It goes through number 1 or number 2. So if they get that and they see, here's a particle. Oh, we just measured it going through slit 1. Where does it hit on the screen? Right behind slit 1. And here's a particle also going through slit 1. Where does it hit? Right behind slit 1. And here's a particle. Oh, look, it just went through slit 2. It lands right behind slit 2, and so on until it piles up big piles of particles behind each slit, just like particles should. But then you stop looking at which slit the particle went through, and the particles will now rearrange themselves in an interference pattern. Okay, so now they'll act like a wave. So that got us to the point that it seemed like what the experimenter did, whether they measured the which way data or don't measure the which way data, will make the light act like a wave if you don't measure it, and like a particle if you do measure it. So the experimenter himself seems to be having some sort of an effect. The choice he makes to measure or not to measure, to get that information or not get that information, makes a difference in how the experiment comes out. You see, well, now that had everybody confused. So why did they do it that way? Why did the system say, well, if they don't know the which way data, then we'll let those particles end up in an interference pattern. But if they do know the which way data, we'll make them just hit the screen right behind the slit. Why would it do that? Well, anything else other than what it did would have created a logical inconsistency between optics and quantum physics. They would have each one would have said the other one was impossible. There'd just been a logical problem between the two. They'd just be logically inconsistent. Well, that won't do. You're trying to make a virtual reality as consistent, as logically consistent as possible. That's what makes a good virtual reality. It's very logically consistent. Virtual realities where the rules change now and again are not very consistent, not good virtual realities. So what it did was it came to the conclusion that it had to work that way to preserve the logical integrity of the virtual reality. Now, of course, that leaves a paradox. How is it when those particles go through there and no which way data is collected that they just magically land on that screen in an interference pattern when there's no forces on them? How do they do that? That's impossible. Well, that's why they call quantum physics weird physics, because it does things that are impossible. Okay, now it's not really weird physics. Once you understand how quantum physics works, it's perfectly logical. But anyway, so if you look at that and you see, all right, here's a problem. Smart little humans figure out about waves and light and how to bend light through lenses and reflect it from mirrors. All right, so it's a wave. Now, even smarter little humans find out a way to send one photon at a time to those same slits. And we know that the photons don't interact. So you're going to have those photons that don't interact are going to have to also go in an interference. But interference what? What interference? They're one at a time. There is no interference. But they have to be put in an interference pattern anyway. Otherwise, there's this logical problem. So this tells you two things. One, that the system is intelligent because they're aware of all of this. Two, that this is a virtual reality because how else could a system make these single particles all going in a straight line just happen to wiggle and wind their way onto the screen and make an interference pattern? Well, because it's a virtual reality, the way you determine what happens next is with a random draw from a probability distribution of the possibilities. So the system took what looks like an interference pattern, turned that into a probability of all the possibilities, and here comes a particle. Where's it going to land on the screen? Random draw from that probability distribution of the possibilities, and that's where it goes. Another random draw, another random draw. Every particle that comes through gets a random draw. That's where that particle goes. And when you're done, well, you get a distribution that looks exactly like the probability distribution you started with, and it looks just like a wave. So that was done. So it tells you that one, that was not an obvious solution. You know, it wasn't that that's just randomly how it works. No, that doesn't sound like random. It sounds like something intelligent made a choice, and the choice was made to avoid a conflict in logic between two pieces of science. So, intelligent choice was made. And how did it arrange to do that? How did it get those particles to put themselves in that distribution? Well, that's the way the reality determines what happens everywhere. You dig a hole in your backyard, and what are you going to find in that hole? Dirt, roots, stones, an old gold coin, a button from your grandfather's vest. What are you going to find there? Well, all of these things are possible, but they all have different probabilities. And what you find there is a random draw from that probability distribution of all the possibilities. That draw comes out, and that's what you've got. Maybe it's a gold coin. Maybe it's your grandfather's pocket watch. Who knows? Something will come out of that. But if it's a gold coin or your grandfather's pocket watch, you probably were lucky to draw something that was, like 1 in 10,000, but you just were lucky and you drew it out anyway. Mostly what you're going to get is dirt, stones, and roots, because the probability there is very high. You see, so the random draw from a probability distribution is not a random draw from the possibilities. It's a random draw from the probability distribution of the possibilities. So the things that are more likely are the things you're more likely to get out. All right, so that's how that works. And to me, to come up with that solution that saves the logical integrity of the system was really the only solution that it could come with. That's the only way to do that. Otherwise, anything else would have created a problem. That was a choice. It takes something intelligent to make choices.
Yeah.
That was a choice. It could have done other things, but it didn't. And there's nothing random about that choice. It's not like, oh, well, that's just how it happens. That choice was made, and the result was created, was affected, so that those particles, for no reason known to man, just distribute themselves in an interference pattern. That tells you this is a virtual reality. In a virtual reality, you can make the outcome be anything you want. You know, you could make those little particles land in a line that spelled a word. It's a virtual reality. You can make it come out how you want it. You have a rendering engine that's rendering it. And if it wants all those little photons to spell out the word LCS, you know, on the screen, well, it could do that if that's what it wanted to do. It's a virtual reality. You can make it do what you want. So it decided to make it do what solved the problem and keep the integrity of the system whole. So that's why I say it appears that just the solution itself tells you that there's an intelligent source making that choice. That choice was not, has to be. There's nothing driving that choice. That's random. Random as opposed to decided. You know, if it's random, then there is no intelligence needed. It's just random. Well, there were other choices, other ways to come out. If it's just random, well, it could be this way, it could be that way, it could be other kinds of ways, but there's only one choice there that comes out that solves all the logic problems. But it leaves a paradox. That's the price. It leaves a paradox. Something impossible has to happen. Well, when impossible things happen, that's a good piece of evidence that you're talking about a virtual reality, because in virtual realities, impossible things can happen very easily. It's not hard to make the impossible happen when it serves your purpose. So that's what I was saying, is that if you look at it that way, it doesn't prove anything. I'm not saying that it proves things. Science really isn't about proof anymore. Way back in Newton's time, they felt that way, but that's because they had very small viewpoints about things. But now we just look for evidence. And that supplies some evidence that you have a virtual reality and the source is consciousness itself, which is conscious. The consciousness system is conscious. That means it's aware. So the experiments that we're going to do next, when we get to them, are going to make even more evidence, because we're going to have experimenters predicting things that are impossible to predict, like how a random event's going to turn out, like a particle that's radioactive and it's going to spit it like an alpha particle out somewhere, and they're going to be able to predict where that particle gets spit out. Well, that's impossible. That is truly a random function. How do you do that? Well, if it's a virtual reality, you can make that particle come out any place you want. Again, you can make all the particles come out and spell a name if you want. It's a virtual reality. So you can do that. And we're going to have a couple of experiments that will allow experimenters to do the impossible, to predict things that are truly naturally random, which will tell you that they're not really random at all. They're produced that way in a virtual reality. And when you have certain information, you can force the system to abide by that information by doing something unexpected. Just like when you have the information of the which way data, you can make it do something unexpected. Now those particles act just like particles. So that's the idea. Now, physicists make up stories, and unfortunately they tend to believe the stories. But they have stories because they realize that that reality is probability and statistics based. And that's true. They got the right answer there. It is. Okay, now nobody knows why it is, but we do. MBT understands why it has to be that way. It has to be probabilistic. It can't be based on material particles. It has to be based on probability and statistics. So given that that understanding that it's probability based, they came up with this thing called the Schrodinger wave equation, and it's not a wave in a physical sense. It's just a mathematical function. It's a probability wave. It's a way of assessing the probability that something is going to be someplace or do something at a particular time. So you're looking at probability. And then they got to the point where they're saying, well, the probability wave collapses to be a physical particle. Well, that's just as silly as saying the particle splits in two, goes through both slits, and interferes with itself. That's obviously just something somebody made up because it sounds good and they don't have anything else to say. They're hard. So they say this, that the probability wave collapses to a physical particle. Well, the probability wave is just a mathematical function. It's nothing real, has nothing to do with the physical universe. It's a piece of mathematics on a sheet of paper, that's all. It doesn't collapse into physical particles. Suddenly, a mathematical function on a piece of paper turns into a massy little particle. That doesn't make any sense. What happens is that when you make a measurement, okay, then you have to get an answer. So if you have a thing that can accurately measure which way data, so here's a little device and it can accurately measure it, and it accurately measures, I've got a particle. Well, then you have to have a particle there. How do you just suddenly get a particle out of no place? It's a virtual reality. You can make a particle be anywhere you want. It's simple. Define a particle, give it coordinates, and there it is. So you put a particle there, and once you have a particle, because the system made a measurement, so because the device, and we know the device works because it always works, we designed it to work. Oh, this device measured a particle here. All right, what's that particle? Well, you take a random draw from a probability distribution and you pull out, there's only one thing to pull out. It's a single distribution, and it's particle. Because that's what the thing was made to measure, and that's what it measured. So you put a particle there. And that particle then travels in a straight line. It's given a velocity, given a position, given a velocity, and it does what particles do. It travels in a straight line, piles up behind the slit. But if you don't measure a particle, then there is no particle, because there aren't any particles anyway. Particles are just a fiction. There never were any particles. So if you don't measure it there, then it's just a proto-particle, a possible particle. And that possible particle will land and put itself into an interference pattern, because that keeps the system logically coherent. So it's the way it works. Now, that sounds to me like there's some intelligence involved in this to make it work the way it works, and that it's a virtual reality. Particles just put places. They're put where they're measured. You got a measuring dice that says, I see a particle here. Then it just wouldn't do for there not to be a particle there. This device just measured one. So of course you put a particle there. And not just any old particle, but a particle going the right direction and about the right size and everything for the particle that's supposed to be there. So that is the way it works. So there's really no particles flying around in the system. When that particle hits the screen and we say, well, it went through the slits, we didn't measure the which way data, and it hits the screen here, we have this vision of a particle flying through a slit, flying through the air and landing on the screen. It's not like that. There are no particles. The system gives it enough time to traverse that distance, and then it just places a particle on the screen at that point from its random draw of the probability distribution of the possibilities. So it says, all right, it's been exactly 5 nanoseconds. We'll stick a particle here. We'll stick another one here and another one here. If each random draw sticks a particle in another place, those particles aren't flying through the air. Those particles are just being manifested on the screen where they're supposed to be at the time they're supposed to be there. There are no particles. It's a virtual reality. Things are put where they need to be when they need to be there. It's just that simple, and you can't have a virtual reality without something intelligent. A virtual reality requires a rule set. It has to have rules. It has to have, the initial conditions of stuff that comes in it and how all that stuff changes and the rules by which it changes. All of that's necessary. Well, that doesn't just randomly pop up out of nothing. That's a lot of structure. That structure just doesn't evolve randomly. So the whole thing makes good common sense that we're talking about an information system called consciousness. It configures a part of itself as a server, a game server, if you will. And it computes, that server serves up a virtual reality that we call the physical universe. And with that idea, now all the stuff that makes up quantum physics becomes more reasonable. And you realize, well, why does it have to be probability and statistics? Because building one up the other way, the other possibility is to start with subatomic particles, build them all up into atomic particles, and I'll rearrange all of those to be molecules and all of those to be matter. That kind of a simulation is ridiculously difficult and unwieldy and takes huge amounts of computer space and time and slow. So why would it do that when it could just make a simple probability model? And of course, it has the rule set. It's got all the rules that there are. So it has the rule set, so it can create those probability distributions perfectly to 10 decimal places if it wants to, or 100 decimal places if it wants to. So it can always create the right probability distributions because it owns the rule set. But it only has to run it once. Once it's run those probability and given it some parameters for temperature or whether it's raining outside or whatever's important to it, then all it has to do is put in the variables, take a random draw, and that's what happens. It's simple. It makes complex things almost trivial to render. And because it only has to render what you can see, that simplifies the problem a whole lot. It's not rendering brains in our heads. It's just rendering our faces. It doesn't have to render anything except what another player can see. That's all it renders. So here we are, pieces of consciousness, playing avatars that have been created in a virtual reality run by consciousness. And once you get that, everything else becomes simple, easy to explain. All those paradoxes fall out as they have very simple explanation.
Well, that's a good theory if it's simple and elegant. Einstein
Yes.
said the answers always should be simple. So that fits a good theory of everything. And that was a wonderful explanation of that phrase that you gave in the physics experiments update and future plans, the intelligence in that process, awareness with a choice in the process of the double slit experiment. That was fantastic.
Well, one of the things that I'd want to add to it would be that this sounds like maybe a very far out explanation of the double slit. But not only does it solve that paradox about how the double slit works, creates a paradox. How do these particles end up in that distribution when there's no force to make them do that? So it answers that question. But if you apply this to all of science, all of physics, you will find that in physics and in even theology and philosophy, social sciences, they all have these paradoxes. things they know to be true, but they have no idea why they should be that way. There's no real good explanation for them. This theory explains every one of them. That is the key. Because if it just explained double slit, you could say, well, anybody could make up something just to explain the double slit. But it not only explains the double slit, but it explains the anthropomorphic principle. It explains just lots of other things. Why the speed of light's a constant, why the speed of light sometimes has little variances in the ninth decimal place. All the things that physicists know about that are true, but they have no idea why they work that way. It explains every one, and it doesn't create another single paradox. It only creates answers to paradoxes, no new paradoxes. And it only comes from one assumption, and that is that consciousness exists. Everything else is derived logically. So given that as a model, and given that level of success with that model, it's almost certain that that model is largely correct. Not entirely correct, perhaps. There may be things that have to be added to it or subtracted from it over the years. I mean, all models are living things. They change as information changes. But it couldn't possibly get that many right answers, creating no other paradoxes or no other problems with the single assumption that consciousness exists. There's no way that could happen without it being largely the truth. So that's the beauty of it. It isn't just that it solves the double slit experiment, because anybody could maybe throw together a story that did that. But if that same story solves 40 different paradoxes in science and philosophy and theology, then that's bound to have some truth to it. It couldn't have that many successes and no failures if it were false. So that's the key thing that needs to go with this expose I just did on the double slit. That's just one.
Of course.
There's lots of those, and that's what makes this the best model around. It's a good model. It's much better than the model they have now, which is a materialist model. That fails immediately to explain how those particles ended up in an interference pattern. So that's an important part to add to it.
That's a well-deserved title, A Big Theory of Everything. And
Yes.
fundamentally, a big theory of everything that covers so much more than just the explanation you gave. Obviously, some intelligence in that process from that video that we'll link below. That was really fantastic. Thank you. Love is the answer. If there's one way to discover this truth that Tom Campbell, physicist and consciousness expert, has concluded, it is through your own experience. Give yourself the gift of experiencing yourself. After all, Tom has stated so many times that if it's not your experience, it's not your truth. So learn to experience with Tom's Exploring Consciousness and Everything Paranormal program, and unlock those natural abilities for yourself. Discover why love is the answer. Binaural beats included to assist you. Details are in the description below. Thank you.
I and MBT Events hope you like this video. If you do, then you should consider being a Patreon member, because Patreon members get early access to our special content. You will also be able to get your questions answered by me in special Q&A sessions, and most importantly, your contribution as a patron member will enable us to produce the content that you're looking for. So thank you.